Okay, let's take a look at these bootcamp problems, and I'll give you some indications on how to do them. So we'll start with number 8. Number 8 and number 9 do have some similarity, so I'm going to do them together. Whoops, let's try again. Sorry, I had the wrong screen open. I'll try again. Right, here we go. Number 8 and number 9. So here we are. All right, now, one important part of algebra is summations. And there are two very important summations that you should know. You should actually memorize these formulas. I'm not much for memorization in mathematics, but there are some things you do need to memorize, like the quadratic formula. Another thing you need to memorize are the formulas for arithmetic sum and the geometric sum. Now, what is arithmetic sum? When arithmetic sum, the terms are evenly spaced. The basic arithmetic sum, oops, it changed, let me change it back. The basic arithmetic sum is 1 plus 2 plus 3 plus ... and let me go up to n. All right, now there's a trick for how to evaluate this, which you should remember, especially if you're a teacher, because it's a very nice illustration. To add this together, add the first and the last term together. It's going to give me an n plus 1. Right, then I add the second term and the second to last term. Second to last term is n minus 1. n minus 1 plus 2 is also n plus 1. ... plus n plus 1. How many of these are there? Well, it turns out that there's n over 2 of them. Why? Because you're taking them in pairs, right? So if there's n numbers here, there's n over 2 pairs. Now, there's a little bit of a glitch if n is odd. But that's okay. It turns out it still works the same way. So here we have n over 2 times. So the result is that if we write in summation notation, I can say sum little n equals 1 to big N of little n, right? This summation expression expresses this sum because the first term is 1, the second term is 2, and so on. So this sum is equal to n plus 1 times n over 2. Right? Now, this allows you to find more complicated expressions. For instance, if I take something like this, summation from n equals, let's say n equals 1 to n. If I have a plus bn, right? I can write this as the sum n equals 1 to n of a plus, now I can take the sum from n equals 1 to n of bn, but if you know, you can take the b outside. Well, I'll do that later. I'll do that at the next term. N equals 1 to n of bn. Just want to make sure I have enough room. I can take the a outside here, and then here I can take the b outside here. Now, this here, what's inside here, this is actually a 1 left inside. Sorry, that's a little bit messy. Let me clean that up a little bit because it's not so nice. We'll just clean it up just a little bit. Okay. Right. This is the sum. Every term here is 1 because I took out the a. All right. So they're n1, so this result is just an. Okay. And this result is plus b times n plus 1 times n over 2. Right? Right. So what you want to do is see if you can cast, for instance, cast this number 8 in this form. It looks very closely related to this basic arithmetic sum, but of course it's not 1 plus 2 plus 3. It's 0.001 plus 0.02, et cetera, et cetera. All right? So you should be able to use this arithmetic sum term to do problem 8. Now there's also the geometric sum. And the basic geometric sum looks like this. 1 plus r, where r is some number, plus r squared, plus r cubed, plus dot, 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 plus r to the n. Okay? So that's the basic geometric sum. Now, if I want to make it a little more general, I can write a here. So that's ar plus ar squared plus ar cubed plus arn. Now, the way you write that as a summation is sum little n equals 1 to big N of a r to the little n. Now notice that I'm not quite right here, because here I don't start with ar. Here I have n equals 1 to big N of ar to the n. If this were correct, then the first term would be ar, but it's not ar, it's a. So I need to fix this. This is sum n equals 0 to big N of ar to the n. Now you can find online, there are often some derivations of this. A nice way to look at this is the sum. I can write this as the sum from n equals 0 to n, from n equals 0 to infinity, sorry, of arn. And then I would subtract the sum from n equals, now I can use the same index here because this is a dummy index. It just applies to this sum. But notice that this n is not the same as this n. It only applies to this sum. So if I want to take out, if I take all the terms from 0 to infinity, I'm including more terms than these. I'm also including the term with r to the n plus 1, r to the n plus 2, and so on. So I have to subtract this out. Okay, and then this would be a r to the n, like this, right? Now, there's a way to simplify these expressions here. This is equal to a times the sum n equals 0 to infinity of r to the n. If you remember, you can take a constant value out of the sum. And then here what I'm going to do is I'm going to take a and r to the n plus 1 outside. And then this changes now. If I take r to the n plus 1 outside, then the first term is going to be ar to the n plus 1, but I took the r to the n plus 1 outside. So the remaining term of r is 0. So this will become n equals 0 to infinity. If this is too quick for you, you can write it down yourself and convince yourself that this is correct. All right. I'm playing fast and loose with this index n because it's inside the sum. It's what you call a dummy index. It doesn't take a fixed value. This n just indicates that I'm changing the exponents here from term to term. All right? All right, now, there is an expression for this summation here, which you can look up. And this is this 1 over 1 minus r. And this is going to be minus a r to the n plus 1 times 1 over 1 minus r. So this is simply equal to a times 1 minus r to the n plus 1 over 1 minus r. Okay? All right. So these two formulas are things that you should know. You should certainly know this. And you should also know that this summation here is equal to this. Those are two things that you should know. Now, how does that apply to problem 9? I will say that this here, it looks kind of funny. A equals 1 to the 1/3 plus 2 to the 1/3 plus 4 to the 1/3. All right. Now, in fact, these are the first 3 terms of a geometric series. All right. So I'm going to leave you with that. These are the first 3 terms of a geometric series, so you can use the geometric series formula. Okay. So for problem 9, here I have 1 to the 1/3 plus 2 to the 1/3 plus 4 to the 1/3 is equal to the first 3 terms of a geometric series. All right? Now, if those are the first 3 terms, you can certainly use this summation formula. That would be n equals 0 to 2. That would give you 3 terms. N equals 0, n equals 1, n equals 2. So you can replace the sum with this formula. All right? So that's going to help you quite a bit. So in this case, you'll need to find what a and r are. Right. Now the other thing you have here is 3 over a plus 3 over a squared plus 1 over a cubed. I want you to recall something. There's also something called the binomial formula. If you have x plus y, right, x plus y, you can use Pascal's triangle. You know that x plus y squared is equal to x squared plus 2xy plus y squared. Turns out that x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And notice these coefficients here, 1, 3, 3, 1, right? These are very important, 1, 3, 3, and 1, right? Now notice that you have kind of this binomial coefficient pattern right here, right? You have the 3, 3, and the 1, and you've got these powers. So what you want to write this, so the hint is to write 3 over a squared plus 3 over a plus 1 using the binomial formula. Okay, so problem 9 is somewhat of a challenging problem, but you can see that you can take these more complicated expressions and use some clever techniques to transform them and rearrange them, and you can get answers much more easily. All right, this is very sloppy. Let me fix this. That's a bad 3. Let me fix that 3 there. Okay, it shouldn't be so nasty like that. All right. Now it's missing a term here, but all you're going to have to do is subtract out the term. Now did I do that right? Or is it 1 over a cubed? Aha, I did it right. Did it wrong. So let me fix the bottom too. Sorry about that. So you're missing one term. There's only one term that you're missing, but the one term that you're missing really has a very simple form. All right, so let's go ahead and do this. So this is 3 over a plus 3 over a squared plus 1 over a cubed. Okay. So what I suggest you do is add 1 and subtract 1. All right, and you'll see that you can get something easier. Now if you do those two things, hopefully you can draw a relationship between those two expressions. Okay, let's move on. Now problem 10, if you go to the sheet and you look at problem 10, I actually did this in the online session. So I think I didn't actually even assign it. Okay. All right, for problem 11, I'll just say rearrange. And I think maybe you'll be able to see there's something that we've seen quite a bit that you'll be able to use. I think I'll leave you with that one. Now for problem 12, let's take a look at problem 12. All right, so I'll grab that here. Give me a second and I'll grab it. Now this certainly looks like it calls for a rearrangement. Right, but here what we have, something very nice here. If you think about things here, when you do partial fractions, let's reduce this fraction as much as we can, right? Okay, so for instance, x plus 1 over x plus 2. Okay, if you do this long division, you'll get x plus 1 over x plus 2, like this. And it goes in one time, all right? And you subtract x plus 2 and you get negative 1. So what does that mean? What that actually means is here we would say that x plus 1 equals x plus 2 with a remainder of negative 1, but that's not really giving us an algebraic equality. What this tells me is that x plus 1 over x plus 2 is equal to 1 minus 1 over x plus 1. Now if you use that fact in all of these expressions, you'll find things simplify considerably. Okay, so what you do is you're reducing the fraction as much as possible, and then you use this and rearrange. Okay, so that's another certainly another algebraic technique is to reduce fractions as much as possible, right? So that's number 12. Let's go and take a look at number 13. I will go and grab it. Give me a moment here to grab number 13. And here we are. All right. Now this looks terrible. You may know how to do, one way to do this is you square both sides, and if you square both sides, you can think about what you get. You get rid of the individual square roots, but that you get a cross term. So then you have to go ahead and square again. Now that's a mess. So let's see if we can use some patterns here to get something better. All right. Now here we have a square root plus a square root. All right. Now we do know something like this. We know square root of a plus the square root of b. One way to get rid of these square roots is multiply by the square root of a minus square root of b. All right? Because then we have difference of squares. Then we get the square root of a squared minus square root of b squared equals a minus b. Nice. Very nice. Okay? All right. So what you can do here is you can multiply both sides by the so I'll just tell you what it is. Multiply by square root of x squared plus 9 and then minus square root of x squared minus 9. Okay? And you get another equation. Okay? So what you can do then is use these two All right, so this will give you another equation. So use these two equations to eliminate one of the square roots. Now once you've eliminated one of the square roots, then you can solve it by a single square operation. Right? Right now you have two square roots. That's nasty. If you square it, as I said, you'll get a cross term. But if you eliminate one of the square roots, then you're good. You just square and you'll be fine. All right? So that's kind of the approach there. All right, let's go on to 14. All right, let me grab it. Where are we? Oops, sorry, I'll have to do it again because I'm not in the right place. We'll get it. We'll get it this time. Go down, put it here, and then grab it. Okay? All right, now let's see. What can we do here? We've got two equations here. We've got one equation here, and we want to use this to simplify that. Now here we have larger powers of a. All right, a to the fourth, a to squared, and so on. All right, so that's not very nice. What can we do with that? Well, we want to use somehow to use this expression on the right-hand side to reduce the order. Now what do I mean by the order? The order is the exponent here. This numerator is order 4. All right. Now what if we rearrange this, we can say a equals 5 minus 1 over a. Now, I don't like the 1 over a. Let's take that out. So here we get a squared is equal to 5a minus 1. All right. Now if you take this a squared, now you know that a to the fourth has an a squared in it. If you take this and you plug it into here, then that a to the fourth is going to simplify. And that a squared is also going to simplify. And the denominator is also going to simplify. So you just keep plugging it in and keep reducing the order. Okay? And in fact, you can plug it in until you only have a to the first power. You can keep plugging this in until all a's are raised to the first power. Okay. Now I think I'm going to stop here and make a separate video for the other problems because there's only so much attention you can spend at a time. So look at these and I'll make another video for the next set of problems and have fun with these.